Operating modern Kubernetes at scale presents a strict physical problem, translating abstract software requests into actual running hardware. When AWS launched Elastic Kubernetes Service, they took ownership of the control plane. But the data plane, the underlying EC2 instances that actually run your containers, remained your responsibility. Today, AWS offers 5 ways to provision that data plane: self-managed nodes, managed node groups, Karpenter, Auto Mode, and Fargate. Choosing among them requires optimizing for total cost of ownership. Every dollar saved on compute cost typically increases platform engineering toil, and vice versa. There is no universally perfect EKS compute model. The right architectural choice requires mapping your exact workload profile against your engineering team's capacity to absorb operational burden. The classic approach is deploying self-managed nodes. Your team writes the bootstrap scripts, updates the operating systems, and manages the Amazon machine images within raw autoscaling groups. EKS-managed node groups reduce that burden. AWS automates the autoscaling group lifecycle and handles rolling updates, freeing your team from manually draining nodes. This diagram illustrates the constraint shared by both legacy models. They rely entirely on the upstream Kubernetes cluster autoscaler to trigger new capacity. The cluster autoscaler does not match specific instances to specific pods. It scales pre-configured groups of identical machines, forcing mismatched workloads to fit into rigid, uniform slots. Relying on autoscaling groups introduces severe latency. New nodes require a lag time of 2 to 5 minutes to boot, register, and become ready to accept traffic. That rigid shape matching traps unused compute capacity inside the nodes. You pay for the entire instance, regardless of how much memory the pods actually consume. Autoscaling groups provide a stable baseline, but their slow provisioning times and imprecise bin packing create strict financial and operational bottlenecks for dynamic platforms. Self-managed Karpenter abandons the node group abstraction entirely in favor of intent-based dynamic provisioning. This diagram shows the mechanism. The Karpenter controller evaluates a pod's exact requirements, like requesting a GPU or tolerating spot instances, and bypasses the autoscaling group. It sends a request directly to the EC2 Fleet API. Karpenter queries the global AWS catalog and provisions the exact right-sized EC2 instance. The correct node boots and joins the cluster in under 60 seconds. This model aggressively optimizes cost. Karpenter continuously evaluates cluster utilization, repacking scattered pods onto fewer nodes, and automatically terminating the empty, underutilized instances. You dictate exactly when this repacking occurs. Granular disruption budgets allow teams to specify whether drifted or empty nodes can be replaced during peak business hours. This efficiency exacts an operational cost. Your platform engineering team assumes total ownership of deploying, monitoring, and upgrading the Karpenter controller, its IAM roles, and custom resource definitions. Self-managed Karpenter provides strict FinOps efficiency and high elasticity. It requires a dedicated, highly capable platform engineering team to absorb the operational overhead. EKS Auto Mode is a no-ops abstraction layer built directly on top of Karpenter's provisioning logic. Here we see the core architectural shift, a redrawn boundary of shared responsibility between your VPC and the AWS-managed accounts. AWS extracts the critical data plane controllers, including Karpenter, the VPC CNI, EBS storage drivers, and load balancers, out of your cluster entirely. They slide across the boundary line into AWS-managed infrastructure. These controllers run as invisible, fully managed system processes. This saves cluster memory and eliminates the toil of manually upgrading these core components to match new Kubernetes versions. At the compute layer, Auto Mode provisions EC2 managed instances that run a customized, highly secure variant of the BottleRocket operating system. This architecture enforces a rigid security posture. Direct SSH access is blocked, and nodes face a strict maximum lifespan of 21 days to prevent configuration drift. AWS charges a roughly 12% compute surcharge on top of standard EC2 rates to manage this automated data plane. You also accept strict technical compromises. Auto Mode prohibits custom Amazon machine images, blocks host-level bootstrapping, and restricts networking entirely to the native AWS VPC CNI. Auto Mode converts fixed engineering headcount costs into a variable compute surcharge. You trade deep architectural control for immediate operational velocity. AWS Fargate takes managed abstraction to its absolute limit. eradicating the concept of an EC2 worker node entirely. This diagram shows Fargate's isolation model. Every individual Kubernetes pod is provisioned inside its own dedicated, hypervisor-isolated micro-virtual machine. No kernel resources are shared. This strict isolation is built for workloads requiring single-tenant PCI DSS compliance, or for highly ephemeral batch processing jobs that execute quickly and vanish, leaving zero idle capacity behind. Removing the node eliminates host-level access. Fargate explicitly blocks daemon sets, prevents GPU attachments, and does not support persistent EBS volumes. Fargate also commands a premium unit cost for vCPU and memory compared to a heavily optimized, right-sized EC2 instance. Fargate delivers pure serverless execution. It works well for teams prioritizing deep isolation, but remains financially and technically prohibitive for running complex, general-purpose Kubernetes platforms. This matrix charts the final decision framework for platform architects. We map the compute models against operational control on the y-axis and workload dynamism on the x-axis. Self-managed Karpenter plots in the top right quadrant. It is optimal for highly dynamic environments where a mature platform team leverages aggressive spot instance strategies and deep EC2 customization. EKS Auto Mode sits in the bottom right. It fits lean teams and startups running stateless web apps, where eliminating OS patching toil justifies the 12% compute surcharge. Managed node groups occupy the top left. They support conventional enterprise workloads and regulated environments that demand custom machine images, but rely on AWS-managed rollout mechanics. AWS Fargate anchors the bottom left. It is reserved exclusively for small internal services or architectures that prioritize true zero-node operations over broad Kubernetes compatibility. This summary matrix provides a final reference point. True architectural mastery in EKS is not achieved by deploying the newest abstraction. It is achieved by strictly aligning your underlying infrastructure with your organization's FinOps budget and engineering tolerance.